this block. Go ahead, Alexis. I'm going to stop sharing.
Thank you, Jose. So welcome back, everybody. I hope you enjoyed chatting in the rooms. So for this next session, we begin with another of our invited talks by Professor Arturo Menchaca Rocha from Institute of Physics at UNAM. Arturo is a member of ALICE and AMS2 collaborations, and he has been interested in heavy ion collisions and production of antimatter for some time. And he has been developing the experimental capacities of Mexican groups from UNAM for over 20 years now. So today he will be talking to us about the production of light nuclei in proton-proton collisions and its relevance to the search for dark matter in cosmic rays. So please, Arturo, go ahead. I'll give you a heads up 5 minutes prior of your time is up. And then when the time is finished, I'll also let you know so you can wrap up. Go ahead.
Okay, I'll share my presentation. Thank you for, let me see if just tell me if you can see, if you see my yes. Presentation. Okay, well, good morning, everybody. I thank the organizers for allowing me to present this, a brief description of what we do. I'm a nuclear physicist, an experimental nuclear physicist, and I feel honored to be invited by your division. So let me see, how do I change my page here? There, okay. So I initiated, well, I'm a member of AMS-02, which now is, as you know, is this magnet dipole installed in the International Station, and I am also a member of ALICE. I formed a group long ago to build instruments for these two experiments. We worked on the development of the aerogel, characterizing the aerogel for AMS, for the AMS reach, and we have developed two detectors for ALICE, the two triggers, V0A and now V0 plus, which you can see here in these pictures. Some of these people you may recognize, especially this fellow here, which is Samuel Ting, and people from who have been parts of my group, and are some of them are important people for other groups in Mexico. Now I try to be provocative, and I was when I joined this with these two projects with instrumental interest in instrumentation, I was naturally faced with the question of if there are common scientific interest for the two experiments. And so I went and read the review of particle physics and found this comment, which I found disturbing. It says that Big Bang nucleosynthesis still marks the boundary between the established and the speculative Big Bang cosmology. That means that after Big Bang nucleosynthesis, or before the Big Bang nucleosynthesis, everything is speculative. I really got interested in that because do we know that if the Big Bang occurred before or after baryogenesis, or whatever happened to dark matter during the, I don't know, okay, and I really don't know. Anyway, the question really is, can ALICE generate data of interest to AMS-02? That's the question inspired me, okay? So something between 1 second and 3 minutes, okay? Long time ago, long before I joined this type of adventures, I had read that the physics of Big Bang and the LHC are occurring very different time scales, but there are since long ago evidences that in both, well, in ALICE being phenomena being so fast, they are still time enough for equilibrium, or thermal equilibrium, and even for chemical equilibrium to occur. This is a picture you might have seen in primary school. This is a calculation using the Wagoner code to reproduce what is the Big Bang nucleosynthesis dynamics. You can see here that in the beginning, once you have protons and neutrons, you begin to have deuterons and even tritons, okay? And way down there, you should have ridiculously absurd amounts of other things. But as soon as this thing thermalizes, well, sorry, the temperature drops at about, I don't know, a few seconds, then the temperature drops below the deuterium binding energy, and then you begin to have important amounts of deuterium, and alphas form, and so you end up with the current composition of the universe, which is mostly protons and alphas, and you have 25 deuterons per million. This all I want to say is that we live in a world, as you all know, that has many more alphas than deuterons. In ALICE, hadronization occurs in a very short time scale, and so there is no time. You have time to produce deuterons, okay, but the production of alphas takes longer, and you just don't have enough. So what happens is that you produce far less alphas, heliums, than deuterons. So this is a very different panorama. Okay, we do observe this type of nuclei. Okay, but they follow. Let's say they follow this different. Just because the time is so short, you have a dominance of deuterons over alphas. And of course, in ALICE, unlike the Big Bang nucleosynthesis, you work in an environment where the baryonic number is zero, basically. Okay, so you have as much matter as antimatter. Okay, now ALICE post-hadronization physics is relevant. This is the domain of nuclear physics, let's say, okay, or nuclear-like physics. And there have been important findings in ALICE related to just quite relevant, no? For example, this test for CPT theorem, okay, by measuring the masses and comparing the masses of nuclei and anti-nuclei, and so you can actually test CPT to very high degree of accuracy, and even the binding energy of this of light nuclei to a very high accuracy, and so what ALICE is relevant to this type of nuclear physics, let's say, which is important. Now, the questions we ask is, how are the deuteriums and anti-deuteriums produced in space? Which is, I mean, I'm trying to relate, as I said, what you learn in ALICE to what you actually observe in AMS. And well, producing deuterons, you have, of course, channels. The lowest energy channel that opens is P plus P, that gives you a positive pion plus a deuteron that has a peak in here. And then you have protons mass plus some other species in the stellar matter that you can knock off a deuteron out of X and produce a Y and a D, and so on. And then at higher energies, you enter in a regime that is basically these are cross sections. So the cross section becomes sort of like geometric, okay? The same happens in your collisions of protons plus helium. You basically have short, low energy mechanisms that produce in these collisions neutrons. Remember, this is all for neutrons, okay? You can produce neutrons from very low energies, and then you enter a high energy regime where you begin to be basically on a geometric regime. You can also produce anti-neutrons, which are, of course, can only be produced by collisions in which you produce proton anti-proton pairs and neutron anti-neutron pairs. And the more energy you have, the more of this you get, and so your production increases with energy. The amount of your cross-section just increases with energy, okay? And the same happens if you make collisions of proton with helium, with cosmic helium, then you will have a very similar situation. The mechanism here is called coalescence, which I will describe here. This is just to make you laugh, no? So you have a phase space, basically. You have a proton and a neutron within a small volume in phase space, okay? And I tell my students that I use Barack Obama catching flies in the Oval Office, okay? In which the probability of catching 2 flies in the same go is just, you can imagine, it's just the square of the probability of catching 1 fly. And that is, of course, depend also on the size of Barack Obama's hand and on the density of flies in the Oval Office, okay? So basically, it's the same thing. The probability of producing nuclei with mass number A, okay, is just the A power of the probability of producing a nucleon to the A power, okay? And this is the parameter that we measure in ALICE, okay, which is the coalescence parameter, okay, which depends on the volume and things. Now there is one to implement this thing where let me just tell you as part of the story. When I joined ALICE and started talking about these things, the Monte Carlo simulations did not consider neutrons as in the stack of possible particles, because nobody really cared in particle physics about neutrons. So I had a student introducing neutrons and introducing the coalescence model, something like a coalescence model into the Monte Carlo simulations in Gen 3 and then in Gen 4. So this was a PhD thesis of Eulogio Serradilla, and then also Diego Gomez Corral did that for other codes. So you really have, let's say, 2 protons that form something that then hadronizes and produces something, but in the way produces a neutron and an anti-neutrons that coalesce and produce an anti-neutron, okay? Now, this is fine in this diagram, but when you the way you implement this model, or was implemented, this model was implemented originally, was that you extracted this parameter from experimental measurements. That means you measured proton spectra, and then you measure neutron spectra, and you divided one by the other, and there you had an experimental, you could extract experimental value for the coalescence, this coalescence volume, okay? But how do you implement that into a Monte Carlo event by event? Is not I mean, you can, since event by event, you cannot do this. So what you do is you actually simulate this by assuming sort of like coalescence, in the sense that you produce all these codes, or many of these codes produce the nucleons in a point. Okay, all the residues are produced in a point. They don't give you they don't give you space distribution. So you assume a space distribution given the in a phase space. Okay, when you have a neutron and a proton that within a given phase space, they are close together, and so they fuse to produce an anti-neutron, an anti-deuteron. Okay, and you add that into the code as an afterburner. So what about AMS-02? What is the interest to do this in AMS-02? Well, in AMS, it was AMS, one of its purposes, or what its aims, is to search for signatures of dark matter. Okay, so they say that a dark matter, if dark matter is made out of particles, then there will be the possibility that you have a dark matter particle annihilating with an anti-dark matter particle, producing something that then decays into regular particles. And in this process, you can actually produce deuterons and anti-deuterons if the energy involved is sufficient to produce a proton, anti-proton and anti-neutron pairs. Okay, and of course this occurs in a background, or the standard model background, of supernova remnant particles that are interacting with interstellar matter, out of which occur what I just described in the previous transparency, interactions that end up producing anti-deuterons. Okay, and this has been this background has been simulated was simulated some years ago, assuming a very simple model. This is the production relative to several possible dark matter candidates. Okay, and it was noted that the detectors, the existing AMS and other detectors, could actually detect this, basically because of the advantage that this standard model background actually has its minimum at low energies. Okay, so but that was deduced from a very simplistic model, this which assumes it makes its following assumptions. Okay, in 2003, the way to produce that prediction was you use the proton and deuteron data to extract the energy, an energy independent element of the coalescence parameter. Okay, let's call it the coalescence parameter. Then you use galactic fusion equation with measured differential cross sections from a Monte Carlo code, and use a geometrical limit, charge symmetry considerations, and coalescence, using this P0 extracted from there to predict the deuteron force, the deuteron flux. Okay. Now, can one do better? That was the question we wanted to answer. And so what we propose is to fit proton productions on all available energies to choose the best Monte Carlo simulator. This is anti-protons, actually. Then you choose the simulator that produces the best values for the measured proton and neutron spectra. Use this parameter to in combination with the Monte Carlo simulator and its afterburner. Okay, to produce neutron production cross sections, okay, and then you use a galactic transport model, okay, to predict the neutron force. This is true for neutrons and anti-neutrons, okay? So all this can be is independent of neutrons and anti-neutrons. Of course, our interest is anti-neutrons, okay? There is a lot of data beginning from Weber-Lack times about the production of neutrons, okay? In various machines, okay, and that takes you all the way up from, as I said, from the Weber-Lack to Alice, okay. So you can use all these set of data to play the game described in the previous picture, okay, and then try and produce predictions for the production of anti-neutrons in proton plus proton collisions at all the energies that have been observed. Okay, so neutrons are produced. This is data are produced copiously in proton-proton collisions, and this thesis of Eulogio Serradilla shows that roughly there is a roughly a ratio of about 1 to 1,000 between the antiprotons to your anti-neutrons, and there is another 1,000 ratio between your anti-neutrons and your mass 3 anti-nuclei, and there is another. So this thing is just a recipe would be that given the number of antiprotons, you can predict the number of anti-helium that has already been measured. I don't have it in this picture. And you always go through about a factor of 1,000. So if you know the spectrum of anti-neutrons, you can predict that that your anti-alphas are going to be about 1,000,000 times smaller. The flux of anti-alpha particles will be about 1,000,000 times smaller than your neutron flux, and that goes for neutrons and anti-neutrons. So as I said, but the procedure is that you choose the best Monte Carlo to reproduce the anti-proton spectra, okay? And here you have we run all the possible codes. Well, not possible, but we had a choice of codes, and some of them make predictions which go very, very far for this production, but some of them that give you a much better reproduction of the experimental data here as the full black dots, okay, at different energies, okay. So so you can actually have a sort of like a best fit, the one that produces the narrowest distribution along the prediction. Okay, so you take differences relative to. Estoy en una conferencia, perdón.
Me llama.
Sorry. Well, sorry. Oops, no puedo. Here, and so you see, I'm sorry, you have a domestic problem here. So EPOS does the best job, as you can see here, by having an RMS of 4.1, and we also use FP for practical purposes. Those were the ones we choose. All others are kind of very far away for our needs. So the Monte Carlo's anti-neutron simulation to extract the P0. So we did this. That was a one. We used that, And so what you really do is that once you have you've decided on a code, you run the code and you see the prediction for antiprotons, let's say, and the prediction for anti-neutrons from the code. You divide the two, and then you have the coalescence parameter. Okay, and so you have made sure that this code predicts the proton spectra, and now you extract the antiproton from the anti-neutron spectra. You extract the P0 value. Okay, you do that for several energies, no, and in all cases, the EPOS and FP work reasonably well. Okay, here they are compared with the old model, the DPyC model, in which cross sections are approximated by a constant P0, and this Gauss-Meyer is a model that actually comes from a fit to all data. So you will always see Gauss-Meyer fitting very well the data, because it's not physics, and it is mostly a fit to the data. Okay, so we did, and we extracted the values of P0, which is is related to the coalescence parameter, except for some constant values, and we saw that we did that for different for different systems, like proton plus proton, protons for beryllium, and protons from aluminum, because you can have these collisions are sources of anti-neutrons in space, in interstellar matter collisions, and from the codes, once you run the actual codes, you can predict the cross sections as a function of energy for all the different from using the predictions. And here you can see, for example, that DPyC overestimates it overestimates the cross sections at low energies, and Cross-Meyer is a fit, so it does very well. But our predictions using EPOS, which you can hardly see the difference relative to FE, it does very well predicting. Okay, so then you use these cross sections and go and use GalProp as this Galactic transport code, and you have well, of course, you have with the different parts of the Galactic code, but this is what is important, is that the neutron sources, you actually you use the result of your cross sections predicted in the way I just described. So you have your spectra here, your cross sections extracted for the different sources. Okay, where all the sources that we included were the proton plus proton, protons for helium, helium plus protons, and helium plus helium, proton, etc. So you have all these possible cross sections, and so you add using this equation, and you end up with the prediction of EPOS, which is this red line, and you compare with DPyC, which is the model that is based on the geometric cross sections, a constant P0. Okay, and Ibarra, which is an effort, a more recent effort that also uses Monte Carlo simulations with other approximations. Then you test your GalProp to compare protons and alphas, the flux of protons and alphas with the parameters you had to define for GalProp, and you see that the protons and the alphas are very well predicted by Galprop using the parameters that you have to define. And so the predicted anti-neutrons from using now the sources that I described. What is that?
5 minutes.
Using what you described. So then this is what you obtain, and to be compared with the first picture of this type that I showed. So you can see that it turns out that doing these proper calculations using for this background, but using not approximated but real, I don't know, the physics that it goes into EPOS and Galprop, you predict a slightly higher cross section all the way, a higher flux. Okay, when you draw it on this other plot, you can see that there is still valid the concept that you have lower energies, you have a better opportunity to detect dark matter particles from different models. Okay, this arrow here marks the contribution, which is actually very small, the contribution from the AMS matter itself, the production of anti-neutrons from AMS matter itself. I will just complement, and I'm about to finish. This is data taken from public talks by something. No, this is the particle spectra from AMS showed last year, where you have between protons and neutrons a factor of about 1 to 200. Okay, this is because, as I said, neutrons can be produced by more channels than anti-neutrons. Okay, and you have again here, if you were to have the same, you would see this, but in fact you expect from our data this to go down at the level of 1,000 between protons and anti-neutrons. So they are consistent with the backgrounds, with the background. What this means is that you have, this is consistent with the coalescent model. Okay, but to be really consistent with the coalescence model, you should see no anti-alpha particles in the, because you would expect that alpha particles would be actually, well, helium particles would be either 1,000 or 1,000,000 times smaller, as described in the thesis by Eulogio Serradilla. But this is another picture from a talk given by something very recently, where this is, hope you can see it. Okay, this compares the anti-proton flux to the anti-helium, measured anti-helium flux. Okay, helium here adds helium-3 and helium-4, and you would not expect to see anti-helium if you don't see anti-neutrons. So anti-neutrons have not been confirmed in the flux, but yet you see anti-helium. So this is a very intriguing result. Okay, because this means that you see more helium than neutrons. So this situation resembles more what you predict, what you would predict from Big Bang nucleosynthesis or stellar evolution than you see from just collisions in space. Thank you very much.
Thank you, Arturo. Thank you for finishing on time. So we have time for questions. Just go ahead and unmute yourself or raise your hand.
Well, I left them speechless, which is one.
So I ask a question regarding I guess I missed the connection. So you described the measurements of this anti-neutron, the measurement of the or I guess the predictions you made for the anti-neutron and this recent or this measurement of the anti-helium not being below the anti-neutron, right? Those are puzzles that you, I guess, are working out. So this, how is this connected exactly with the, how does this help the searches for dark matter that can be done with the AMS experiment, for example, or in the colliders? Exactly, I didn't quite catch that.
Well, if the signature comes in the anti-neutron channel, okay, since we are going to have a hard time at the AMS level, because we are not convinced. I mean, right now the anti-neutron flux is consistent with the background. This means you are producing anti-neutrons. Remember that what I showed is the background to dark matter signal, to a dark matter signal. Okay, so no dark matter signal. Well, no anti-neutrons have been published, at least not as far as I know, even found, no, okay, confirmed with convincingly, okay, above background. So all I can say at the moment, okay, is that one has to wait longer now. And this is, if you ever heard Samuel Ting keeps saying that whenever he's asked, when are you going to present the results for alpha particles or for anti-helium, and he says as late as possible, okay, and that is the reason, okay, because he doesn't really, I mean, he wants to to wait until the end of basically until the end of the International Space Station to accumulate the highest possible statistics, okay, and that is basically, I think, my interpretation. But so at the moment, there is we know what to expect from the background. So answering your question directly, we say nothing about dark matter directly, but about what would be the background to dark matter. This is what I try to convince you.
Right, which is pretty crucial to know the background of.
Well, better than before. Well, I say that had already been calculated by estimated by somebody else, but they had not done it, let's say, with all the power that simulate Monte Carlo current Monte Carlo simulations have. Heidi.
Yes, thank you.
Thanks, Artur. Heidi, yes, go ahead.
Yeah, thank you. Well, my question is regarding the solar modulation. I've seen that many works have different ways of accounting for the solar modulation. And I was wondering if the choice is important for certain analysis, or if there is a more concrete way to do it.
Okay, well, that goes into the Galprop. Galprop is a code, just like Giant and all these things. And you can include you can or cannot, is a choice in the code to use solar modulation. We did introduce solar modulation. I'm not an expert on this, okay, so but I can tell you is that in running our code, okay, solar modulation was included, okay. Now solar modulation is important at low energies, but anti-neutrons produced in collisions of primary cosmic rays with interstellar matter, as I showed in my picture, have a peak at energies which are well above the solar modulation in the solar modulation regime. So solar modulation would tend to move a little bit up and down the low energy part, okay, but the low energy part is already small enough, as you saw, that there are about, I don't know, several orders of magnitude less cross sections than the predictions for dark matter. So solar modulation, it does influence the background, but as far as I can tell, it's not a big, it's nothing to worry about. We need to detect anti-neutrons. Anti-neutrons should be more abundant if dark matter existed or were to be detected in AMS with a strong signal.
Yeah, thank you.
Thank you for your question, Adi.
Any other question for our speaker? I don't see any raised hands. So remember, you can, if you have questions, you can talk to Arturo and the other speakers in the chat rooms in the next break. So let's thank Arturo and move on to our next speaker.
Thank you.
Thank you, Arturo. Good to see you.
Right.
So our next speaker is America Morales from University of Guanajuato. America, are you there?
Yes, I'm here.
Please go ahead and share your screen.
Yes, thanks.
I guess we need Arturo to unshare his screen.
I think it's already, you're already seeing my screen.
Oh, sorry, I think I made a mistake. In order to not to break the order of talk, I think the next speaker should rather be, I'm sorry, Ms. Heide Hernandez.
Yes.
We already tried your talk, so sorry, let's move back to the correct order and try Heide first. I apologize. Heide, can you share your screen?
Yes, I'm going to. Can you see it now?
Yes. Okay, so our next speaker is Heide Hernandez, also from the University of Guanajuato, but also helped me with the confusion. She's going to talk to us about spin 1 dark matter and gamma ray signals from the galactic center. Please, Heide, go ahead. I'll give you a heads up 5 minutes prior to the end of your time.
Yes, thank you. So what I'm going to talk about is a work that we are trying to explain a certain excess of gamma rays in the galactic center. Well, we already know, I'm not going to explain it in detail, but dark matter is a mystery in terms of the particle physics. And even though it's 5 times more abundant than the baryonic matter that we can describe, but we have certain observations and properties that we have to take into account in order to propose candidates that may explain this energy. Relic density, direct and indirect detection limits are among those. In the standard model, we have various representations of the homogeneous Lorentz group that we use to describe particles. For example, a scalar like the Higgs may be explained as the 0-0 representation. Quarks and leptons are explained as the 0, 1/2 plus 1/2 0 representation of the group, etc., etc. Extensions may include other types of representations like the gravitino or the graviton. And in our case, our proposal is to use a space-time structure in the 1-0 plus 0-1 representation. These have fields that are described by a 6-component spinor, and it turns out the kinetic term is not chiral, and that prompts us to use that as a way to describe dark matter. This formalism is explained in detail in these works. The first one is more general, and the second one is a approach from the dark matter theory side. But what's important is to look into the interactions that this type of dark matter will have with standard model particles. For example, we have these two interactions with the Higgs, either with a pair or a singular Higgs. And the couplings that describe this interaction are what we call the Higgs portal. We call them GS and GP. And there's also interactions with the photon and the C boson by this tensor, and we call that the spin portal of this theory. And the coupling that describes it is GT. In that work that I mentioned, one of the important conclusions is that if we look into the direct detection limit by xenon 1T, which involves neutron and dark matter collisions, we see that the spin portal coupling is much severely constrained than the Higgs portal one. And this is important to take into account for what I'm going to talk about next. So the purpose of this work is to try and explain this excess of gamma ray flux in the galactic center that is around the 3 GeV energy mark. There are several studies that have found this excess, and there are many ways to explain this excess. It could be astrophysical sources, but we are interested in the explanation by dark matter annihilation with a photon or photons in the final stage of the process. For our theory, we have 3 basic processes that have a photon in the final state, dark matter annihilating into something and a photon, a pair of photons, or into a pair of fermions and then radiating somewhere in the process. And we can calculate the differential flux with these expressions. As you can see, this part of the expression that is not between parentheses includes all the information of the model. And the part between parentheses is what we call the J factor that involves the density profile of the dark matter and the details of the observation. Now, the first 2 processes have quasi-monochromatic spectra, which are important, but in order to explain the excess, we need to take into account or look more into the third process that has a broader spectrum. And there is a work that I put here that found that this excess can be explained by that process, dark matter annihilating into a pair of fermions. But for this mass range, 5 to 174 GeVs, the cross-section of the annihilation needs to be of this order, 10 to the minus 26. And here I plot, for our case, the values of the cross-section. As you can see, to achieve that value of the cross-sections that we call the thermal cross-section, because it turns out it's also the order of the magnitude that we need to explain the relic density, we need to be around or near the Higgs resonant limit, which is the mass being half of the Higgs. This is, of course, taking only the Higgs portal interactions, because the spin portal are severely constrained by xenon 1T, as I explained. So for this process, we have mainly 3 types of radiation. The first one, initial state, is severely constrained because it's of the order of GT2 square. So this is constrained by xenon 1T. And in the tier 1, this one that has a quarkonium, which is basically QCD corrections, is non-sizable even on resonance, so this will not contribute. And this other one that has a photon or a C boson in the middle only contribute to the higher end of the spectrum. It's important to take into account, but the ones that are going to explain the excess are the final state radiation ones. And there are 3 types of process. The first one is the direct emission, which is simply calculate that diagram. Or we can have a production of photons by decay products of the leptons, or hadronization of quarks. Now, we use these packages, Dark SUSY and PPC4, to calculate these fluxes. And we can see that in the case of electrons and muons, if we take only the direct emission or the decay products, there's barely any change because electrons and muons don't have hadronic decays. So the only change comes from higher order electroweak radiative correction, so there's barely any difference. But for the rest of the fermions and leptons, there is a difference, and we need to take that into account. So summarizing these contributions, we see that the flux, the gamma flux that we obtain from this, what we call the prompt photon flux, has a major contribution from B quark pair annihilation. And in the higher of the spectrum, we have contributions from internal radiation, as I mentioned, and a little bit of the tau pair production. And we can see that this is already sizable enough to explain the excess. However, there is another process that produces gamma rays, that is the delay emission or inverse quantum scattering. And this can come in three ways. First could be electrons propagating after being produced directly from annihilation, or maybe propagation of electrons but that are produced as decays of the leptons from the annihilation. And we also have propagation of muons. Now, the first one is negligible because the couplings are very small for electrons. And the third one is small in this mass window, so it will not contribute as much. So what we're left with is the second one. We see here the electrons barely contribute. The muon is below what we need. And the major contributor is, again, the big quark and a little bit of the tau quark pairs. So taking everything, every contribution into account, we have that we can explain this gamma ray excess for this mass window that I put here, and for these values of the coupling of the GS coupling. And again, the major contributor is the B pair, and but the rest of the contributions are also important. Now that we have explained the excess, we need to see if the rest of the constraints are satisfied. First, we start with the relic density. Now, in the previous work, we had used an expansion, a non-relativistic expansion for the cross-section, because we were at the resonance, so there was no problem. But now that we are at the resonance, we need to use the complete expression for the cross-section, because as you can see here, let's take, for example, the red curve. The dashed one is if you use the expansion, and the solid one is if we use the complete expression. As you can see, there's a lot of difference when we are near the resonance. So we need to use a complete expression. And when we do that, here I'm plotting the value of the coupling that is consistent with relic density. The previous work that we use expansion is the dashed blue line. As you can see, it's a very steep fall. But when we use the complete expression, the curve changes. And if we compare it with the xenon 1T limit, we see that near the resonance, we have a region that is well satisfied for both constraints. So we are okay with that. There are other bounds, for example, annihilation into muons or taus, and we are well below these bounds. I'm not going to talk about that. Simply, we have no problem in that regard. However, when we see limits to B quark pairs, where that is our major contributor, we run into a risky territory, because the limits, we are right there in the limits. We are between the 95% containment for the limit. And this work here is obtained by combining an analysis of the energy flux from 45 dark spheroidal galaxies. Now, from those 45, only 19 targets have a J factor that was derived experimentally from observations of stellar dynamics. So we wanted to see that in detail. We used that those 19 targets. I don't know if you can see here, but there's like a white band here. This is the energy flux from our theory, and the black lines are the limits for those that specific target, right? Using likelihood function data that is provided by the experiment. And we can see that for our highest value of matter, which is the riskier value, we are well below those limits for these 19 targets. So we are safe in that for that limit. There are other constraints, for example, a gamma pair production from annihilation, and we are also within the 95% containment. So you can see we are well within the constraints, but lowering these bounds will tell us something about this model. Now, to summarize, taking into account all the contributions to the gamma ray flux, we can explain that the excess in the galactic center for these values of the coupling at the mass. These are in agreement with relic density and with xenon 1T limits. We also have agreement with constraints from annihilation into muons and taus and into gamma pairs. Even annihilation into B quark pairs when we take into account a detailed beam by beam analysis of the 19 targets of the galaxies. But lowering these limits, the B quark pair and the gamma pair bounds, will give us the definite test as to if this space-time structure that we are using is a good possibility to describe dark matter at this mass magnitude. You can see the full work in this publication, and thank you for listening.
Thank you, Heidi. Thank you for finishing right on time. Are there any questions? Okay, so there are not any questions. I didn't check the list. In the interest of recovering the couple minutes we're behind, let's thank Heidi, and remember you can ask her questions in the chat rooms, the breakout rooms, and let's thank her again, and let's move to the next speaker. Thank you, Heidi.
Thank you. Thank you.
Okay, and now our next speaker is Ms. America Morales from University of Guanajuato. And she will be talking to us about neutrino mass generation models.
Yes, thank you for the presentation.
Go ahead.
I will talk to you about some models of neutrino mass generation, mainly on the Skeletogenic Model and some extensions of this model. And I hope to give you some general idea behind our work. So I'm going to start with the standard model. We know that the standard model is a theory that contains the fundamental building blocks of ordinary matter, and it's a gauge quantum theory with this gauge symmetry. It has 19 parameters, and it contains 17 building blocks of nature, 6 of which are called quarks, 6 are the leptons. We have four carriers particles and a Higgs boson that gives masses to some of these particles. And with these ingredients, it is possible to compute a huge number of processes that involves interactions between particles and fields. However, there are some physical phenomena in nature that the standard model cannot explain. For example, nature of dark matter, neutrino mass, neutrino nature, some others. I will focus mainly on these first two. So the standard model explains about 5% of the energy and matter present in the universe, but about the 26% should be dark matter. Yet the standard model does not supply any fundamental particle that are good dark matter candidate. So it's a big issue in the standard model. And another important question is about the nature of the neutrino. If neutrino are or aren't their own antiparticle. If they are, we can say that they are Majorana particles, and the dynamical equation will not be the Dirac equation anymore. So there's a big change in our model where all the fermions can be described as Dirac spinors. But if neutrinos aren't their own antiparticle, there will be Dirac particles. And there are some way to investigate if neutrinos are Dirac or Majorana. Due to this process, the neutrinoless double beta decay. And some experiments like NEMO 3 in France or Cuore in Italy are made to observe this process, neutrinoless double beta decay. Also, another important question in the standard model is the origin of the mass of neutrinos. So according to the standard model, neutrinos are massless particles. However, neutrino oscillation experiments have shown that neutrinos do have mass. And in fact, their flavor states are a mixture of their mass eigenstates. And then, since neutrino oscillation data only allow us to know the mass square differences, the absolute values of their masses remains as a mystery. That's why we need to account for neutrino mass generation models to solve this puzzle. So some models of neutrino mass generation are the seesaw mechanism that we have 3 types of this mechanism, and another like the Skeletogenic model. I will briefly talk about the seesaw mechanism, and I will focus mainly on the Skeletogenic model. So the seesaw mechanism is the most popular mechanism of neutrino mass generation and describes the smallness of neutrino mass as a resulting of induced from fermion exchange. This model have a simplest version that is type 1 seesaw mechanism that corresponds to having the neutrino mass induced from fermion exchange, like this first diagram. And the type 2 seesaw mechanism is where the neutrino mass are generated by adding a weak scalar triplet to the standard spectrum, like this, this other diagram here. But another interesting model for how neutrino masses is the Skeletogenic model. There is a minimal extension of the standard model where it's extended by adding this symmetry, the zeta-2 symmetry, and the observed left-handed neutrinos obtain naturally small Majorana masses for from a one-loop radiative mechanism like this diagram. And in this model, it has 2 candidates for dark matter, one bosonic and one fermionic. And neutrinos remain massless at 3 level in the standard model. So that's why it's called Skeletogenic, because the neutrino masses is created from dark matter sector. And well, in this model, the particle content is this one. where it has a neutral fermion N and a single SU2 doublet eta that are odd under the zeta2 symmetry. And we can notice that the standard model particles are even under this symmetry. And the additional zeta2 symmetry prevents eta to have a non-zero vacuum expectation value and allows these two fields to act as dark matter candidate. So the neutrino mass term in the Skeletogenic model has this form where HEK and HGK are the Yukawa couplings of the process, and MR square and ME square are the imaginary and real components of the mass of the field eta. So the Skeletogenic model is a very beautiful model because it allows us to obtain naturally small neutrino masses and candidates for dark matter in just one model. So we can explore some other scenarios extending this Skeletogenic model. And one of these is where dark matter stability is interconnected with the directness of neutrinos. And in order to do this, we built upon a minimal extended class of single value shelter 331 model, or SBS 331 model, and we extended to with another symmetry U1. So in this case, we have what we call Skeletogenic 3311 model. And the unbroken B-L symmetry acts as a protecting symmetry responsible for both the Dirac masses and the stabilization of dark matter. So here in this figure, we have the matter content of the model, where additional to the original SBS model, we have included two-component Majorana fermion singlet SR, like this one, and a scalar anti-triplet Phi4, this up here. So the Yukawa interactions allow the one-loop contribution to the neutrino masses via this diagram. Assuming that the Majorana mass of the fermion singlet SR is already diagonal, the neutrino mass matrix generated by the Skeletogenic loop is of this form, and the neutrino Dirac masses has this other form that is consistent with the original Skeletogenic model. It's also appears in here the Yukawa couplings and the imaginary parts and real.
5 minutes.
Okay, so another kind of extension to the Skeletogenic model is this other one, where we proposed a scenario where we consider the case of a gauge unbroken B-L as dark matter stabilization symmetry. So in order to promote the accidental B-L global symmetry of the standard model to a local one, we need to extend the standard model field to ensure the anomaly cancellation. So the way that we do this is the inclusion of 3 right-handed neutrinos with a B-L charge of -1. And this is enough to make the model anomaly-free and then consistent. So we suggest 2 standard model extensions with a gauge B-L and dark matter as the mediator of neutrino mass generation. That's what we call Skeletogenic B-L. And we have 2 models. The first one, the model A, is where we add a new doublet eta and a singlet sigma in the scalar sector, both are charged under Big-Mono cell symmetry. And in the fermion sector, we add the 300 neutrinos, nu R, as well as the gauge singlet fermions SR. And like a variant to this model, we propose the model B that differs from the first one due to the introduction of 3 extra fermion fields SL, this or from here. So the Yukawa-Lagrangian models for model A and B are this of here, and in both cases, the neutrino masses have the same form, like this one, that is, it has the same form of the original Skeletogenic model. But for the model A, MS key, this one of here, are the eigenvalues of the Majorana mass matrix, while for the model B, the same MS are the Dirac mass matrix eigenvalues. So these are the diagrams of the one loop for the two models, and we can say that the internal fields at the loop, they are odd under matter parity, while the others are even. So if the lightest matter parity odd of these fields are stable and electrically neutral, it can be a dark matter candidate. And then we have two options. We can have a complex neutral scalar or a fermionic dark matter candidate. If it's the fermionic, we can have two options. If that is a Majorana fermion or a Dirac fermion. So as a conclusion, we need neutrino masses generation models to solve some problems in standard models. An especially attractive possibility is that neutrinos, the mass of the neutrinos in dark matter have the common origin. So that is the Skeletogenic model. And we have extended the Skeletogenic model in two ways. One way is adding a new symmetry in the SVS331 model. And the other one is to have an unbroken Big-Mono cell local symmetry. And in this way, the symmetry is responsible for the Dirac nature of neutrinos and the stabilization of dark matter, the dark matter candidate. And that's it. Thank you.
Thank you, America. Thanks for being on time. So we have time for questions. I guess Wolfgang has a question. Please go ahead, Wolfgang.
Yes, you mentioned that this Skeletogenic model provides naturally light neutrinos. Could you explain again why they are naturally light?
Because the way that they have masses is upon a loop, radiative loop. So this process is already small.
But loop contributions can run up to the cutoff scale naturally, isn't it?
Sorry, what?
Loop contributions naturally run up to the cutoff scale.
Yes.
Yeah, okay, it's okay.
Remember that there will be a chance to talk with the speakers at the chat rooms. Any other questions? Okay, if not, let's thank America once more And let's move on to the last speaker of our session, who will be Guadalupe Moreno Granados from Simba staff. She will be talking to us about neutrino electron scattering radiative corrections in short baseline experiments. Please, Guadalupe, go ahead and share your screen. I will give you a heads up 5 minutes prior to the end of your time.
Okay, thank you. Can you see my screen now?
Yes.
Yep, excellent. Thank you, Alexis. Hi, everyone. Well, I will talk about the neutrino electron scattering radiative correction in a short baseline neutrino experiments. Here is the outline of my talk. First, I'll give a brief motivation for studying the neutrino electron scattering. Then we move to the radiative correction and the effective neutrino charge radius of this process. I'll present an example of a short baseline experiment where we estimate the number of events that we expect to get considering the radiative correction and the neutrino charge radius as well. And finally, some conclusion of this work. So this work is based on this preprint. So if we want to see for more details, you can do it. Okay. So first of all, as we know, the standard model has been shown to be a good precise theory. So this theory has been verified in several physical observables by multiple experimental collaboration, like Gargamel, Tevatron, Babar, Bell, LED 1 and 2, currently the LHC, Bell 2, and many, many other experiments. So due to the fact that we are in a period in which it's necessary to perform precision tests to verify the standard model predictions, and therefore be able to search new physics in a reliable way, in the neutrino sector, we have several dispersion processes that involve them. So one of these processes is the neutrino electron scattering. So this is a purely leptonic process that can provide us with several precision tests in electroweak parameters, like the precise measurement of the weak mixing angle, for example. Besides, this scattering process play a very important role. Its pure leptonic character has been helpful to provide clear signatures in different prediction of the standard model, such as the existence of neutral currents, for example, in Gargamel experiment of CERN in 1973, as we can see here in this figure. So on the other hand, most of the next leading order radiative correction can be evaluated analytically, and therefore we can serve as a prototype for more complicated cases of scattering, such the neutrino nucleus scattering, for example. So in the neutrino sector, once the neutrino oscillation mechanism was confirmed by Takaki Kajita and Arthur McDonald, the experimental development has been amazing. So, and it's expected that high precision measurements will be taken in the near future. So in this context, it's necessary to check the standard model prediction in these experiments in order to perform new physics searches reliably. So in particular, the search for the existence of the CP violating phase motivate the construction of long baseline experiment like Dune, that it's a Fermilab experiment that will be consist of two neutrino detectors. The FAR detector will be located at Stanford Underground Research Laboratory at 1,300 kilometers downstream of the source. And a near detector will be set up near to Fermilab. So those long baseline experiments predict intense high neutrino beams, and the possibility to measure the neutrino oscillation properties with high precision. So on the other hand, for the neutrino, for near detectors, open the possibility to measure the neutrino electron scattering with high statistic. With this, give the chance for its precise measurement. So, okay, now we'll focus on the mu neutrino electron scattering, that is a neutral current processes mediated by the Z boson, which only involve leptons, as I mentioned before. This process can be test of the standard model at low energies of the weak mixing angle and the possibility existence of an effective neutrino charge radius, for example. Here we have the Feynman diagram of this process at 3 level. And here we have the differential cross-section at 3 level as well. For this equation, we can see that the coupling constants, GL and GR, are defining like this. So where the theta W is the weak mixing angle. So, but now if we move to the next leading order, the radiative correction of the neutrino scattering can be divided in two, depending of their dynamic origin. One of these correction is the electroweak, the QED correction, which involve the creation and the absorption of the photon in the electronic current, as we can see in this diagram. And on the other correction is the electroweak correction that are due to the exchange of W and Z bosons, as we can see in this diagram. So now the expression for the differential cross-section, considering this both contribution of the radiative corrections, we have this expression. So where the contribution of the QED correction are into these F's functions, while the electroweak correction contribution are into this new coupling constant that actually are not constant anymore, because now depends of the electron recoil energy. So here we can see the dependency of this electron recoil energy is in these kappa factors. So I talk about a little more in the next slides. So here, for these expressions, we have that the sin square of the weak mixing angle now is calculated in the Z mass scale. So the rho NC factor has this numerical value, and the kappa nu L factor sorry, is defined by this equation. So where the L, the subline is L, represents the neutrino flavor, that in this case we only consider the mu neutrino. So this expression also is in terms of the Q square. That is the square of the for momentum transfer. So, okay, so now if we focus on this kappa factor, we can see that its flavor dependence contribution is only in this term. That if we evaluated this kappa nu L factor in Q equal to 0, usually this quantity is associated with the neutrino charge radius and becomes to this expression. So if we plotted this kappa nu factor, we get this red line distribution. While now, if we consider the kappa nu factor without the neutrino flavor dependency, we give this equation. And if we draw it as well, we get this blue distribution that actually is very similar to what we observe in the PDG. So one thing that we can see is that the fact that the additional contribution due to the neutrino charge radius down the shape of this distribution, principally in this part. So that is very interesting. Now, if we focus only on the shaded region, in this region, which is the region where we perform our analysis, we estimated that the difference between the two kappa's values is approximately 3%. But okay, so this is our theory. But now, what happened in the experiment? So I present here a short baseline experiment for which we perform our analysis. This experiment called PRISM, and it's a near detector configuration option for Dune. So PRISM is characterized by using the same technology as the Dune
5 minutes.
part detector. Yeah, thanks. For the part detector in Stanford. And also this is a movable detector that allows collecting data at several off-axis angles, as we can see in this cartoon. So PRISM expect to have 75 tons of liquid argon. And for our analysis, we consider a period of 3.5 years running in the neutrino mode and the same period running in anti-neutrino. So as we consider this movable detector, this allows getting different fluxes and spectra, as we can see in these both plots. This is considering the fluxes for the neutrino beam mode, and this is for anti-neutrino beam mode. Again, is considering several off-axis locations. So for the following example I will show, is only considering the on-axis case. So here we get a comparison among the number of events expected at the tree level, that is the solid black line. And the dashed red line is considering the neutrino charge radius contribution. And the blue line is without the neutrino charge radius contribution. So for both modes, neutrino and anti-neutrino beam. So if we focus on this particular case, the anti-neutrino case, at low energies, the first beam shows a good possibility to measuring the radiative correction and even the neutrino charge radius. Now, if we consider the difference of the total number of events at tree level and with and without the neutrino charge radius contribution, and compare between the tree level statistic error, we can see a very good opportunity to measure this radiative correction and even the neutrino charge radius. So again, this behavior, we can see it for both cases, the neutrino and the neutrino. So with these results, we can conclude that the neutrino beam mode, due to its higher statistic, will allow a better determination of the radiative correction and the possibility to measure the neutrino charge radius. But it is only if the systematic errors are under control. So, well, for the anti-neutrino case, compared with the neutrino mode, our analysis showed a good possibility to measuring the radiative correction and even the neutrino charge radius with the lower energy beam. So this is a very interesting result. So a very happy result. So it will be interesting to test in some experiments. So, okay, that's all. Thank you very much. If you have any questions, comments, are very welcome. Thanks.
Thank you, Guadalupe. Are there any questions for the speaker? I think Juan Barranco has his hand raised. Go ahead, Juan.
Hi, thank you very much for the talk. When you are saying that in the last sentence, you say that lower experiments with lower threshold will be with a higher sensitivity. Which kind of experiments are you thinking?
Well, well, the first experiment that we think is this PRINCE, that we expect to have a higher statistic, but it's only the consideration for the future. The current experiments that I set up and actually taking data is Icarus, for example, the SBND, or those facility experiments at Fermilab. Actually, that is one of the tests that we want to prove in those experiments. But unfortunately, we think, well, we estimate that the systematic errors and the sensibility of those experiments they're not to be the sufficient sensibility to measure these properties. So, but of course, is just think to prove and see what happened.
Thank you very much.
Yeah, thanks.
There's a question in the chat from Newton Nat.
Yep.
Can you go ahead and ask your question, or I can read it out for you?
Yeah, I can ask the Guadalupe, what happens if you combine neutrino and anti-neutrino data?
Oh, actually, we didn't try this. Actually, it's a very good idea. But, well, the idea to separate it actually is because, let me see, we have some contribution, well, different contributions for the neutrino mode and for the anti-neutrino case. And here we have the rate of the different cross-section, so defining like this. So here we can see that the electroweak correction have different behaviors for the neutrino, that is the upper line, and it's different the behavior of the anti-neutrino case. But I think if we combine it, maybe this correction maybe will be equal to 0. We lose sensitivity. So maybe that is the answer. That why we don't combine it, both results. Yeah.
Okay.
Mm-hmm.
Thanks.
Yeah, thanks to you.
Okay, is there any other question? And I guess as a related comment, probably there's an easy way to combine the observables, as Newton suggests, for neutrino and anti-neutrino, you know, so that they don't cancel out, like taking like the sum of the squares of the squares of the contributions, or something like that. So you will gain the statistics from each of the two. So.
And also, oh, sorry.
Yeah, go ahead.
Also, this is for online, on axis, right?
Yeah, this is a case of for on axis, but actually same analysis we're done for off axis cases. And actually we look that when we move to where we move more for off axis case, we lose this number of events. Actually I don't remember if it's 0 for 1.8 degrees, we lose this sensibility. So yeah, actually it's working better when we are in on-axis case.
Anyway, can you show me the flux plot?
Yeah, sure.
So this on-axis, it is around 2.3 GeV, right?
Yep.
And this which one corresponds to the second oscillation maxima for the off-axis?
Oh,
like this 0.6, 1.2, these are arbitrary or corresponding to second oscillation maxima, one of them?
I'm not sure. Wait, the maximum oscillation, I don't know. Yeah, maybe it's in this part of the region energy.
The maximum is for 2.6. This is for 1 axis. It is fine. 2.
Yep.
Okay. Anyway,
you say that this part, sorry?
I'm talking about like 0.6, like Dune has also second oscillation maxima, right?
Yep.
So motivation to take this 0.6 off axis is to look for the second oscillation maxima or what? That is my point.
Oh, okay, I got it. Yeah. Yeah, that is the motivation. Yeah, to be different angles in moving to 0.6 degree. Yeah.
Okay, anyway, thanks.
Yep.
Okay, so I don't see any more hands raised. Remember, we can chat with the speakers in the breakout rooms, and we have just reached the end of the session. So let's thank our speakers of this session, and I yield control to Jose if he can tell us how to move to the break. And thank to all the speakers of the session and all of you.
Hi, yes, so we are now at the lunch break. So we will have, let me just share.